We're diving into the world of CPUs, those tiny chips that power our computers. But before a single circuit is etched, it all starts with a blueprint, a detailed plan. Engineers carefully design the CPU's architecture, like deciding the layout of a bustling city. They determine the functions of different units, much like zoning areas for housing or businesses. This design phase is critical, folks. It determines how fast, efficient, and powerful the CPU will be. Imagine trying to build a city without a planned chaos. Similarly, a well-designed CPU is key for smooth and speedy computing. The design is then translated into a language computers understand, using complex software tools. Think of it as converting the city blueprint into a three-dimensional model. This digital representation guides the entire manufacturing process, ensuring each microscopic detail is in place. Without this intricate design phase, we'd be lost in a silicon desert. It's the foundation upon which the entire CPU manufacturing process is built. Now, let's move on to creating the base material, the silicon wafer. Believe it or not, the journey from a beach to your computer chip begins with ordinary sand. Sand contains silica, which is purified and transformed into a single crystal of silicon. This process is like growing a giant, flawless diamond, but instead of sparkle, we're after conductivity. The purified silicon is melted and then slowly pulled upward, forming a cylindrical ingot. Picture pulling taffy, but instead of sugary goodness, we're stretching a super pure silicon crystal. This ingot can be several feet long and perfectly uniform in structure, ensuring consistent electrical properties throughout. Next, the ingot is sliced into thin, round wafers, like slicing a loaf of bread, but much, much thinner. These wafers are incredibly thin, often less than a millimeter thick and extremely fragile. Each wafer will eventually house hundreds or even thousands of individual CPUs. These shiny silicon wafers are the foundation of our CPUs, ready for the next stage of the manufacturing process. Hold on to your hats because things are about to get really small. Now that we have our silicon wafers, it's time to print the intricate circuitry. But we're not talking about your average inkjet printer, folks. We're entering the nanoscale world of photolithography, where light etches microscopic patterns. Imagine projecting the CPU design like a miniature movie onto the silicon wafer, but instead of a screen, we use a light-sensitive material called a photoresist. This photoresist changes its chemical properties when exposed to ultraviolet light. A mask, containing the desired circuit pattern, acts as a stencil. Light passes through the mask, exposing specific areas of the photoresist on the wafer. The exposed areas harden, while the unexposed areas remain soft and can be washed away, leaving behind the circuit pattern. This process is repeated multiple times, layering different materials and patterns on top of each other. Think of it like building a skyscraper, floor by floor, with each layer contributing to the final structure. Photolithography is the key to creating the intricate network of transistors and connections that make up a CPU. Section 4. Etching and doping, sculpting the circuitry. With these circuit patterns precisely defined by photolithography, it's time to sculpt the silicon wafer and create the actual transistors. This is where etching and doping come in, two processes as essential as a chisel and hammer to a sculptor. Etching is like using a tiny, high-precision sandblaster. Chemicals selectively remove unwanted material from the silicon wafer, following the pattern defined by the photoresist. This creates the trenches and channels that will eventually form the transistors and interconnects. Doping involves introducing impurities like boron or phosphorus into specific regions of the silicon wafer. These impurities alter the electrical properties of the silicon, creating areas that conduct electricity differently. This controlled doping is what allows transistors to switch on and off, forming the basic building blocks of digital logic. Through a combination of etching and doping, we transform a blank silicon canvas into a landscape of interconnected transistors ready to process information at lightning speed. Section 5. Layering up material deposition. Our CPU is starting to take shape, but it still needs more layers to function correctly. Just like a house needs walls, insulation, and wiring, a CPU requires various materials to connect, insulate, and protect its delicate circuitry. This is where material deposition comes in. Think of material deposition as carefully applying layers of paint to a masterpiece. Different materials, like metals for conducting electricity or insulators to prevent short circuits, are deposited onto the wafer in precise patterns. One common method is chemical vapor deposition, where gases carrying the desired materials react on the wafer's surface, depositing a thin film. Another technique is sputtering, where ions bombard a target material, knocking off atoms that then settle onto the wafer. These layers build upon each other, creating a complex three-dimensional structure. They provide electrical connections between transistors, insulate different areas to prevent interference, and form a protective barrier for the delicate circuitry. Without these crucial layers, our CPU would be like a house with exposed wiring, a recipe for disaster.